About all things in this amazing universe, because that's exactly what this show is about. We record every Thursday at 8 p.m. Easterns, and you can follow along online or leave a voicemail at spaceradioshow.com. And in today's Blue Shift, I'll be talking about the reality of diversity in physics. But first, the news. Hey, Space Cadets, welcome to Space Radio. I'm Paul Sutter, astrophysicist at Stony Brook University and the Flatiron Institute. And for the next half hour, your agent of the stars, we've got an exciting show for you today where we talk about all the amazing things in this universe. This show lives on listener questions. We record every Thursday at 8 p.m. Eastern here at Spaceman Studios in New York City. So you can leave a voicemail at spaceradioshow.com to get your voice on the air, or join the Space Cadets tuning in live from around the world, including but not limited to Portsmouth, UK, Florence, Massachusetts, Deer Park, Maryland, Sussex, England, Kempner, Texas, Washington, D.C., Germany, Howell, New Jersey, New Zealand, Nashville, Tennessee, Ashburton, New Zealand, Phoenix, Arizona, and Austin, Texas. I'll answer questions that you send there too. Seriously, the Space Cadets probably have more fun than I do, and I've only prepped 10 minutes to show material tops, so get those questions in. Space Cadets, good to see you again. Hope you've been having a good week. Whew, we've got some good news. We've got some fun news. No, I'm just kidding. It's not fun. It's not fun at all. Gosh, James Webb is delayed. I know. Bring in your questions, Space Cadets, so I can answer them in the show. Thank you so much, Nancy, for wrangling them as always. You do such a great job. I really appreciate it. Give a shout out to Nancy. Sorry, just handling some life stuff. There we go. Thank you, Nancy, for promoting the book, How to Die in Space. It's my new book. It's out nationwide, audiobook, ebook. Go to Amazon, Barnes & Noble, all the usual. Let's do a show. Oh, yeah, I need my timer. I always forget my timer. My little timer's on my phone. Here we go. Before I start taking calls, I want to share some interesting bits of news I caught recently, and two bummer things. One is out front, a bummer thing, and the other is really a bummer thing, but disguised as a cool thing. The upfront bummer thing is, that whole James Webb Space Telescope thing, supposed to launch in March of 2021. Well, guess what? Yeah, it's gonna be delayed. What did I tell you, folks? Everyone's like, no, Paul, you're just being a pessimist. No, I swear it won't be delayed this time. No, listen, they ironed out all the bugs. They got it. We figured it out. It's delayed. No one knows when it'll launch. I mean, I'm sure there's a date floating around out there. Don't believe it. I don't think this thing will ever launch. I don't think the James Webb Space Telescope will ever launch, because I'm just an ultimate pessimist when it comes to this. Sorry, I just need to center myself. I was getting too much negative energy, which is different than dark energy, okay? You can be filled with dark energy. All it does is make you get bigger. Anyway, the other bummer news that was disguised as exciting news is I saw all these headlines this week about astronomers discovering a planet around a star where the planet is a lot like Earth and the star is a lot like the sun, and the planet is in the habitable zone of the star. So here we are, a potential Earth 2.0, except not. Okay, so the sun is 10% brighter than the sun, or 10% more massive than the sun. Okay, that's great. Planet is indeed in the habitable zone. It's the third planet in the system. It's not confirmed. I should say it's not confirmed. We don't have direct observations of this planet. What we have, how they actually found this planet, is very clever. We had Kepler data, the Kepler Space Telescope, found two planets around this star using the normal transiting technique where the planet blocks a little bit of the light from the star. Then we dug into the data a little bit more, like years later, and found that there are tiny little variations in how often those planets orbited the star. And those could only be due to the presence of other planets that are tweaking and pulling on the orbits. This is a technique called transit timing variation, or TTV, if you like saying words like that. With this technique, astronomers suspect that there might be two more planets in this solar system. Kepler 160, I believe, is the name of the system, also known as KOI 456.04. If you want to plug that in and start colonizing it, go right ahead. It's pretty far. It's like 3,000 light years from the Earth. It's not confirmed. It's not confirmed. But if it is confirmed, there is a planet in the habitable zone of a star that's a lot like the sun. This planet is twice the size of the Earth. So it's like, fine. Yes, they did some modeling. Yes, they did some analysis. Yes, if it does have an atmosphere like the Earth, it's a little bit farther from its star than we are from the sun. So things balance out, and it looks like it's warm-ish. The Earth has an average temperature of 15 Celsius. This planet would have an average temperature of 5 Celsius, which is above freezing. I guess that's nice. But still, it's twice the size of the planet Earth. So who the heck knows what is going on? And to me, that's more of a bummer than a cool thing, because we haven't actually found an Earth-like planet yet. We got to keep looking. We got to keep looking. Anyway, that's the latest and greatest when it comes to space. Let's have a conversation. I know, right? Just a mess. Yeah, we got some cool voicemails. I'm gonna try and hit a couple voicemails if I can. Super strong aliens, that's what we're gonna get. Like ripped, because they're big massive planet. Like they'll come to Earth, they'll be like Superman. Isn't that how Superman worked? He came from a planet that was had stronger gravity than the Earth, so it was just like lightweight for him. I don't know. Someone will correct me. All right. We've got a lot of voicemails ready to go. So, hey, Greg, why don't you pick one and play that tape?
Hi, Paul. Steve here from Aberdeen, Scotland. The universe is expanding. Space-time is expanding. My understanding of space-time is that the dimension of time is inextricably locked in with the three spatial dimensions. Does this mean that time is expanding along with the spatial dimensions? Do we have to take this into account when we are measuring, for example, the age of the universe? Thanks, Paul.
This is a really fun question, Steve. Thank you so much for asking. Yes, we learned from Einstein's relativity that space and time are linked together. You can only think of space-time. We live in a four-dimensional universe. There are 3 dimensions of space and 1 dimension of time. We also learned that the universe is expanding. How does the expansion of the universe fit in with our 4-dimensional view of the universe? Here's the thing. The expansion of the universe is only an expansion of space. It is not an expansion of time. In our cosmological models of our understanding of the Big Bang and the history of the universe, time marches forward. There is a universal clock. There is a clock that sets the age of the universe. And then at a particular time, the universe is a certain size. So in the past, at some measure of this cosmological clock, our universe was smaller. Then today, at this measure of the universal clock at 13.8 billion years old, it is this big, 90 billion light years across or something like that. And then in the future, at future times on this clock, the universe will be larger. It is only the spatial dimensions that are expanding. And it is the march of this universal clock that is telling you how big the universe is when, depending on how old it is. So this is allowed. Einstein tells us that time and space are indeed linked, but they don't have to be. Depending on the particular physical system, like, say, the entire universe and its expansion history, the spatial dimensions can go off doing their thing, while the time dimension goes off doing its own thing. And that's exactly what we see in the universe. Really, really fun question, Steve. I really appreciate it. I think we got a little bit of time for another question. I don't know. I'm feeling good. I'm feeling spunky. Greg, play the tape.
Hi, Dr. Sutter. My name is John. I'm from Seattle. I have a question for you regarding the Higgs field. I've heard it said that the potential energy of the Higgs field in a 1-inch sphere of empty space is roughly equivalent to the mass energy of the Earth. I've also heard that the event horizon of an Earth mass black hole would form a sphere that's approximately 1 inch. That seemed like a big coincidence. Is there a real connection between the energy density it takes to make a black hole and the potential energy density of the Higgs field? Is the Higgs field related to black holes in some way, even though it's not related to gravity? Thanks for taking my question. I'm a big fan of your work.
Oh, this is again a really fun question, John. I really appreciate it. This is asking about the fundamental nature of our universe and vacuums and energy densities and black holes, and gets into all these super, super, super interesting questions about things that we don't fully understand. It is true that if you take the Earth, in the whole mass of the Earth, and squished it down to a sphere a little less than an inch across, you would have an Earth mass black hole a little less than an inch across. That's all you do to make a black hole. You just take a bunch of stuff and squish it down to be really tiny. It is true that if you have an empty box with nothing in it, you have a lot of energy. There's a lot of energy in the vacuum of space-time itself. And I know that sometimes these are just like random words that don't have any meaning. And feel free to treat it as such. Just know that the vacuum of our universe, a state with absolutely no particles in it, has a lot of raw, bare energy in it. You can't use this energy for anything. You can't use it to do work or to heat things up. It's just there. It's just the ground state of our universe has a bunch of energy inside of it. Technically, the amount of energy in the vacuum is, well, infinite. Immediately, that starts to feel a little bit uncomfortable. But that's what all of our mathematics and our observations tell us. How that energy is divvied up amongst the various characters in the universe is going to have to wait for after the break. I love teasing it. I love cliffhangers. Sorry, it's just going to be how this works. We are gonna come back after a quick break. Don't forget to leave a voicemail to join the conversation or to join the Space Cadets live at Thursday at 8 p.m. Eastern. Go to spaceradioshow.com for the links. This is Space Radio. I'm Paul Sutter, and this show is brought to you by you. Please go to patreon.com/PM Sutter. That's P as in Paul, M as in Matthew, Sutter as in Sutter. Patreon.com/PM Sutter. It's your contributions that keep this show on the air, and I will see you after the break. All right. I know. For you YouTubers, Space Cadets, and whoever listens on the podcast, you're just going to get it really soon. But if you're on the radio, listening on the radio, you just have to listen to a little commercial break. Sorry about your luck. Okay. And then I'll finish this question. Thank you, Nancy, for wrangling as usual. Oh boy, so many questions. I'm gonna try to do just go through these as quickly as possible. We're gonna do on there the marathon. I think you guys like the marathon. I have a lot of fun in the marathon. I'm ready. My neck's a little stiff, but I think I can do it. You guys ready? I'm not ready. Welcome back, everyone. I'm Paul Sutter, and this is Space Radio. We've got so many more cool questions ready to go, but remember, you Yes, you can join the conversation by leaving an online voicemail or by following the live streams. Check out spaceradioshow.com for all the links. Before the break, we were listening to John ask a question about the vacuum energy of space-time and Higgs fields and black holes. Technically, there's an infinite amount of energy in space-time. That's not very helpful. How it's divided up between the various characters in the universe is a matter of, let's say, convention. You get to kind of randomly decide how much energy the different fields have, how much mass they have. When it comes to the Higgs field, the Higgs particle has a certain mass. The Higgs field itself, it can have whatever kind of energy it wants. So these connections between Higgs field, vacuum energy, black holes are a little bit specious because you're just, at some point, you just have to make up definitions. And if you make up definitions in the right way, you can get things to line up in interesting ways. But they're only interesting because you kind of set it up to be interesting. So I'm going to go ahead and say there's not really a strong connection there, except there's a lot we don't understand about the vacuum energy of our universe. Now, moving on to our space guest, we got Thunderduck on YouTube asking, why do some people think the moon is made out of cheese? What? It's not made out of cheese? I don't understand this question. I'm just going to move on. Optimist Narkill on YouTube is asking, what are my thoughts about the newest repeating fast radio burst that was found? It's a signal every 157 days. What do I think it could be? Okay, so there's something powerful happening roughly every 157 days. Okay, nature makes weird stuff. I don't know what it is. It's probably something blowing up on the regular. Nature can surprise you with how regular she can be. I'm going to guess it's natural because that's the safest bet. Justin Engel on YouTube is asking, does the tendency of dark energy to try and resist expansion constrain its spatial spread and increase its density, causing it to have more explosive effect like an overfilled balloon? Good question about dark energy. This is the accelerated expansion of our universe. Everything we know about dark energy says that it is constant. Its density is constant. If you have a certain volume, you're going to have the constant density of dark energy, which will give you a total amount of dark energy, say in this room I'm in now. And then if I compare my room to my house is going to have more dark energy because there's more volume, but the density will remain the same. So the universe is getting bigger and bigger. The density of dark energy remains the same, but the volume of the universe is going up, which means the total amount of dark energy is going up. And this is actually what counterintuitively is driving the accelerated expansion of the universe, is the fact that you get more dark energy today than you had yesterday. It could also be that the density itself is going up. We're not exactly sure about that. That's a scenario called phantom dark energy. If that's true, the universe will rip itself apart in 5 billion years. So let's hope it's not. Chris Delney on YouTube is asking, when we're trying to figure out the age of the universe, do we take into account something called the surface of last scattering? The surface of last scattering is the visible limit of our universe because past that, the universe is too thick, too much of a plasma, it's too opaque for us to see. The actual edge of the universe is just past that. We get the age of the universe not from this, but from our model of the Big Bang, from our cosmological models, informed by data, informed by things like the cosmic microwave background. We plug those in to get the ingredients of the universe, and from there we can tell you its age. So the more we know about what's inside the universe, the better we're able to pin down its age. So basically, to answer your question, yes, we take it into account. Another question, Prime JD is on Twitch, advice for a grad student preparing to go through Jackson E&M. So the physics textbook on electromagnetics is written by Jackson. I can see it on my bookshelf right there. I see it right down there. Jackson, electromagnetics. Any advice? Read it. do all the homework problems and listen to your professor. It's not an easy book, but it's not an easy topic either. It's just like, if you want to give yourself an education on electromagnetics as a physicist would, go buy this book. It's Jackson, Electromagnetics. Good luck. Good luck. All right, moving on. Julius on YouTube is asking, why does the distribution of stars in the universe, it doesn't follow a standard distribution? Why are there far more red dwarfs than other stars? Yeah, like something like 2/3 of the stars in Milky Way are red dwarfs, these tiny little things half the size of the sun. The reason that smaller stars are more popular is that they are far, far easier to make. In order to make a big star, if you want to make something that's like 20 times the mass of the sun, you need to get a lot of stuff together in the right space, collapse together without blowing away, without getting irradiated. It has to collapse. That is a tricky thing to do. It's just really, really hard to make big stuff. But it's really easy to make a small star, something like half the mass of the sun. You can do that without even breaking a sweat. So it's like asking, why are there so many more 2-story buildings than 20-story buildings? Because it's a lot harder to build a 20-story building than it is to build a 2-story building. Moving on. Yamagishi-san is asking, why don't neutron stars become black holes? Neutron stars don't become black holes because there is something resisting the collapse of all that material. That something is a very strange and exotic force called quantum degeneracy pressure. Definitely not going to get into it. Suffice it to say that it can resist being squeezed down. And so all that material in a neutron star, it's super dense, it's super crazy, can't quite squeeze down all the way to become a black hole. Now, if you start adding mass to it and piling on, you can break that degeneracy pressure and you can get yourself on the road to black holedom. Moving on, Zach on YouTube asking, is Pluto a planet? Here's the thing, folks. I'm going to lean back from this. I know I'm a little bit farther from the microphone because I want to be a little casual right now. I think Pluto should be a planet. I said it. Look at the pictures. Look at the pictures. It has like nitrogen glaciers and an atmosphere and water ice mountains. It might have a subsurface ocean. Like, it's cool. It's hot on the inside and cold on the outside. If you just showed me a picture of Pluto, or you just went to some like uncontacted tribe and said, hey, do you think this is a planet? After you explain the concept of a planet, you say, do you think this is a planet? They 9 times out of 10, they go like, yeah, that's a planet. Why are you even asking me? What a lame question. It looks like a planet. That's my argument. Acts like a planet, quacks like a planet, walks like a planet. It's a planet. That's all I got. So many more Space Cadet questions, but unfortunately, we are almost out of time here on Space Radio. But before we go, it is time for the Blue Shift. Woo! That was a fun marathon. I'm looking at you, Jackson, E&M. That is a beast of a book, let me tell you. There's some other... Basically, all physics textbooks are horrible. Basically. All right. We gotta take it down a notch. We gotta be a little bit serious. I'm Paul Sutter, and you're listening to Space Radio, and this is the Blue Shift, my opportunity to get a little bit closer to you. And I know that you have heard about, perhaps participated in, thought about, conversed about the unrest that our country is seeing, about Black Lives Matter, about racial injustice, about police brutality. I've been doing a lot of thinking, and I wanted to share some another angle of this, another angle of racial injustice, another angle of how minorities like Black students have a tougher time in our educational system and moving up in the ranks of our educational system than you might think. Because a lot of universities, a lot of institutions which I'm a part of, put on a good face. Say yes, we are welcoming. We to Black students, to minority students, to women, to everybody. But then when you look at the numbers tell a little bit different stories. So I wanted to share some numbers and some thoughts on those numbers. Not everything, not all my sources are up to date to 2020, so we're just going to take what we have. For example, in 2004. In 2004, across the entire world, there were 1,186 PhDs in physics awarded. That's 1,186 PhDs in physics awarded in the year 2004. About half of those were in the United States, half were in the rest of the world. Of those 1,186, 13 were awarded to Black Americans. That's a deliberate pause there. Of over 1,000 PhDs awarded worldwide, 13 were awarded to Black Americans. That was 2004. If we look back the past 30 years, there were a total of around 35,000 physics PhDs. So, there's about 1,000 new physics PhDs awarded every year. Total in 30 years. In 30 years, Black Americans were awarded 288 PhDs in physics. 30% of those were in the past 6 years. It's not much better for bachelor's degrees. In bachelor's degrees in 2015, there were a total of 7,329 bachelor's degrees in physics awarded in physics. Of those, 175 went to Black Americans. And here's something else. This number hasn't really changed in 20 years. This number hasn't changed. African Americans, Black Americans are getting roughly between 150 and 200 bachelor's degrees in physics every year since the mid-90s. Here's the thing. There are more than 13 Black Americans who are more than smart enough, capable enough, intelligent enough, good enough to earn a PhD in physics. There just are. Why aren't they? How are we failing Black Americans when it comes to higher education? Why aren't they interested in physics? If they are interested in physics, why aren't they applying to good undergraduate schools? And if they get a bachelor's degree, why aren't they applying to good PhD schools? And once they're in the PhD system, why aren't they finishing? Why are there so few Black Americans in higher education, and especially my fields like physics and astronomy? When they're smart enough, they're out there. There are young Black kids who could be the next Einstein, who could be the next genius. Maybe one of these kids has figured out how to unify physics, but he or she doesn't get a chance because we've let them down. I don't have solutions right now. But I just wanted to present another angle on this. And unfortunately, this broadcast is almost done. Thank you for joining me on this voyage of space radio. Once again, I'm Paul Sutter, and this show is brought to you by you. Please go to patreon.com/pmsutter to learn how you can contribute. But if you'd rather not contribute this month, please go to discoveryrise.org. It is an organization that I'm contributing to, discoveryrise.org. Thanks to Greg Moebius for producing, Nancy Graziano for England, the Space Cadets, and all the fine crew at WCBE Radio 90.5 FM in Columbus for making this show possible. Catch the live stream every Thursday at 8 p.m. Eastern, and visit spaceradioshow.com for more info and links to the live stream. And of course, thanks again, Space Cadets, for listening. See you next week, and remember, science is for sharing. End of transmission. And Space Cadets, I think I'm going to skip the cheese tonight. We'll do cheese again next week. Instead, we should just have a moment to reflect, hopefully, about what we can do.